I welcome you all in this lecture on simulation of simple pendulum. So, which is a sub module for modeling and simulation of dynamic system course through which you are going through. Here essentially we want to see the simulation examples, and in this lecture we will see that how can we use the Simulink as a simulation tool to simulate a dynamic system, and that dynamic system we are going to take the simple pendulum as the example, and of course we will be taking many more external effects on the simple pendulum, such as we can consider, or we will be taking the effect of drag or effect at the effect of friction at the pivot and so on. So, here you can see this figure illustrate the simple pendulum, okay, where say m is the mass of the bob, and there is a say a string here of length L from the centroid of this mass, and of course there are certain drag forces are assumed, and say this is my axis through which I measure this angle. Now, the simple analytical model for a standard pendulum can be derived by assuming the no drag force and a small variation in the angle of the pendulum. So, we will begin with the simplest possible case, and then we will go on making our model more and more involved. Okay. So, here initially, as I said, we will assume that there is no drag force acting on the bob, and we will be taking this small variation in theta. Okay. And we can assume that the entire mass of the pendulum is concentrated in the bob, and that the length from the pivot point to center of the gravity of the bob is given by L. Okay. So, first we can say write the equation of motion for the bob, and that we can do by taking the moment around the pivot point O, and of course the counterclockwise we take positive, and of course you know that this tension is not going to cause any moment, because this T is going to pass through this pivot point. So, actually what we are going to do is that we are going to write the equation of motion for this one. Now, you see in this example, say this is our bob, and this length is actually the length L. Here this is weight mg, this mass is m, and this is my reference axis with respect to which, say, I measure this angle theta. So, for writing the equation of motion, what we do is essentially we write the torque acting say here about this pivot point. Okay. So, to do that, what we can do is that we can resolve this force, that is weight, into a component along the length of the rod or string, and another, say, perpendicular to this one. So, since this angle is theta, this angle is going to be theta. So, this component will be actually mg sin theta. Fine. So, now this mg sin theta force will be causing a moment here. Okay. So, that moment will be given by mg L cos theta. Okay. And since this moment direction is clockwise, that is opposite to our convention of taking the positive value of theta. So, I put a minus sign here, and I equate this to that is I into theta double dot. Okay. So, this is the inertial torque, and of course, this is the unbalanced torque which is acting on the bob. Okay. So, this alpha is basically the theta double dot, and I, of course, we know that the mass moment of inertia of the pendulum I is given by ml square, and the angular acceleration of the pendulum alpha is second derivative of theta. So, alpha is equal to theta double dot as I have written here. So, I can simplify this dynamic equation okay, as this one. I can take this to that side. So, what I have is ml square theta double dot plus mgl sorry, this is mg sin theta here. So, this is not cos theta, this is mg l sin theta. So, ml square theta double dot plus mg l sin theta, this is equal to 0, or I can write it as theta double dot plus I divide it by ml square. So, I get g by l sin theta is equal to 0. So, this is my dynamic equation for the pendulum. Okay. So, it is this equation theta double dot plus g by l sin theta is equal to 0. Okay. So, this is the dynamic equation for the pendulum. Now, this equation you can see that this is a non-linear equation. Our aim is to find out the theta as a function of time, but you can see that this equation is non-linear because of the sin theta term. Okay, that is, it has a transcendental function. So, this non-linear equation can be linearized or converted into a linear equation if we assume that this theta value is small, and we know that for a small value of theta, the sin theta is same as theta. Okay. So, we can linearize this equation by assuming the small value of theta. Okay. And of course, as I said, for a small angle expressed in radians, sin theta is approximately equal to theta. So, our equation turns out to be this one, theta double dot plus g by l into theta is equal to 0. Okay. And this equation describes the dynamic behavior of the pendulum. Okay. Now, this equation, you can see that this is a second order differential equation. So, this equation can be solved by many ways, but here we would like to solve it using the Laplace transform. That is, initially we will convert this differential equation into an algebraic equation in S domain, and then find out the value of theta in S domain, and then we will again take back the inverse Laplace transform and bring that solution in the time domain form. Okay. So, this can be done. So, the equation which I am talking about is our basic equation, that is theta double dot plus g by l theta is equal to 0. Okay. And you know that in our lecture on the Laplace transform which we were discussing, you see the Laplace transform for a second derivative is given as s square Laplace transform of the function minus s into the value of function at say t is equal to 0 minus value of the derivative of the function at t is equal to 0. Okay. So, in this case, suppose if I assume that the pendulum is released from some initial angle, say theta 0, and there is no initial velocity. All right. So, first let us write a generalized expression for this one. So, theta double dot I can take help from above equation, and so theta double dot I can write its Laplace. I can take the Laplace for this. So, this is s square theta s corresponding to this term, minus we will have s here, and here we will be having the theta 0 value, and this term I am taking this as a 0, okay, because I am assuming that there is no initial velocity. So, this term will be 0 here, okay. So, this is there, plus we have g by L into theta in Laplace domain, and that is equal to 0, okay. And now from this equation I can solve for the value of theta s, okay. So, this theta s will give me s theta 0 divided by s square plus g by L, okay. So, this is what I get for the theta s value. All right. Now, I can convert this solution from Laplace into the time domain by taking the inverse Laplace. Now, you see here what we are getting is s theta 0 divided by s square plus g by L. So, this is basically s upon s square plus omega square form. All right. So, the Laplace transform for some constant k into s by s square plus omega square is given by k cos omega t, okay. So, this is given. So, I compare this expression with this one and take the inverse Laplace for both the sides. So, this becomes my theta t, and of course, I have theta 0, and this value will be in the Laplace that is from taking inverse Laplace will become cos of omega will be here. Basically, if I compare this, then omega is my under root g by L. So, this is under root g by L into t. So, this way I can write the general expression for theta, that is theta is equal to theta 0 cos under root g by L into t. So, this is my general solution for this expression. Now, to visualize this function, okay, for comparison purpose, we can make a simple Simulink model here. So, say I have a clock, and clock signal is given to this is actually the square root of g by L, which is a gain basically, all right. And then I take the cosine of this term. So, here basically I get this term, and I take a cosine of this one, and then I multiply this with the theta 0 value. So, I have the theta 0 value from here, I multiply this, and this is what I get the theta. So, here is my theta, and then of course, I can use my radian to degree conversion using the simple formula, that is theta by pi is equal to d by 180. So, my d will be 180 by pi into theta. So, using this formula I can convert radians to degrees, and I can see that value of theta here. So, this way I can simulate the behavior or simulate the behavior of the pendulum in terms of the rotation theta. Then let us try to make the model a little involved. Let us assume that our model is non-linear, okay. And how do we assume this non-linearity? That is, the previous case we remove the non-linearity by assuming the theta value to be very small, okay. So, I removed that assumptions from here, okay, and say I say that my theta value is not small, okay. So, we can create a Matlab Simulink model to solve for this equation. Okay. So, this is our equation. Of course, as I said, I am not taking my theta to be smaller here. Okay. So, this is my basically equation which I want to simulate. Alright. So, here you can see that say let us say that this is the point where I have the theta double dot value. Okay. So, I put an integrator here 1 by s, I get a theta value here sorry theta dot value here, and of course, I put a display here to see that. Okay. So, that I am calling say as omega. So, this is my theta dot value. I further integrate that by say using integrator 1 and I get a theta here. Now, this theta is in radian. I put a gain basically in order to convert the radians to degrees, and of course, I can view that theta value here. So, here I have got the theta value. Now, I put a sine function here. So, basically I will be getting this sine theta here, then this sine theta I multiply by g by L here, okay, through this gain. So, I get here g by L sine theta, and again you see that we have got a minus sign. So, I put again a gain here with the gain as minus gain block with the gain as minus 1. So, this is what I get minus g by L sine theta, and this is nothing but the same theta double derivative. Okay. And the rest of the say steps are repeated. Okay. Now, let us take further complicate our model by taking the non-linear model including a constant aerodynamic drag force. So, let us assume that there is a constant aerodynamic drag force Fd is acting on the bob. Okay. Now, we can assume that the aerodynamic drag force acts only on the bob and the drag on the thin rod is negligible. The drag force imposes additional moment about this point O, as we can see from here. So, now if I want to write the differential equation governing the dynamics of the pendulum, what are the unbalanced moments? First I write and then I will equate it to the inertial moment. Okay. So, the unbalanced moment here, as I was telling, mgl sine theta with a minus sign opposite to our assumed positive direction of rotation of the pendulum, minus this Fd into this length, as I said, is L. So, minus LFD, and this is our I alpha, or this is ml square theta double dot. Okay. So, this way we can write that, and now I can simplify this equation. So, this is our basic equation. Alright, this is our the moment because of the drag, and of course, this is moment because of the weight of the bob, and this is the inertial moment. Fine. Now, we can isolate the highest order derivative here. So, our theta double dot, I divide both sides by say ml square. So, this is what I get, minus g by L sine theta. Of course, m and L, one m and this L gets cancelled. So, I have minus g by L sine theta minus I am dividing this term by ml square. So, I have minus 1 by ml into Fd. Okay. And corresponding to this equation, I can prepare a Matlab Simulink model. So, this Matlab Simulink model I can realize here. Of course, again we go by this expression. Okay. Now, here you see, say this value is my theta double dot. I take a first derivative here. So, I get omega 1. Okay. And then I take second I take the first integration here, the integrator 2, I get that is omega or theta derivative theta dot, and then I take another integration, I get the theta value. Okay. So, here again the radian to degree conversion, and of course, we have got the display, and here we have the theta value, then I take the sin theta. This model is similar to what we have seen previous in the previous slides. So, I have sin theta and then I multiply with g by L and I take a minus sign here. So, what I get the minus g by L from here. Now, this we have to model this term basically. So, to model this term, what I do is that, say I have got the drag force Fd. Okay, I will explain this a little later. So, I have this Fd, and this Fd I divide by 1 by ml here, and then I put a minus sign here. Okay, and both these added up here will basically give me the theta double dot. So, here I get this theta double dot term. Now, you see that this drag force actually changes sign based on the angular velocity of the pendulum. Okay. So, here although the drag force is taken as constant, it must always act opposite to the direction of motion. So, to take care of that, here we have we take the omega here, and of course, we put a sign here, and then this is given to be multiplied with the Fd value. Okay. So, this is how it is done. Then let us further add further features to our model. So, here the non-linear model including aerodynamic drag force, that is a function of velocity. The previous one we had the constant drag force was assumed. Now, we can take, if my drag force is a function of velocity, so I can write the expression for the aerodynamic drag force for incompressible flow over any body, and of course, this is given by CD A rho V square, where CD is the drag coefficient, A is your frontal area, V is velocity, and rho is the density of the fluid. Now, the drag coefficient for the cylindrical body, of course, is a function of Rayleigh number Re, which is given by rho Vd by mu, of course, where mu is the viscosity. Okay, viscosity of the incompressible fluid, and d is the diameter of the cylinder. Okay, other terms we have defined. So, we can use the standard literature available in order to find out the CD value for a given Rayleigh number. Okay, this is basically Rayleigh number is expressed in terms of the kinematic viscosity, which is basically nu by rho. Anyhow, for a given Rayleigh number, we can find out what is the value of CD is going to be, and that CD value can be substituted back. So, to create the Matlab Simulink model, we have these three expressions. This is expression for Fd, and here there is a CD term, and of course, this CD I get from the plot for the Rayleigh number versus CD. Okay, so, I get the CD value, I get the Fd, and then I can substitute this Fd in this expression in order to create the Simulink model. Okay. So, rest of the things are same, because we are building on the basic model only. So, here we have theta double dot, first integration here. So, I get the theta dot, second integration I get the theta, and I view the theta here in the display. I have get the sign here, then g by L being multiplied by g by L. So, this is there, the minus sign here, the same thing. Okay. And this portion also we have discussed the same as the previous case. The only thing is that this KD is determined now, this yes, Fd, sorry, this Fd is being determined now from here, okay, before being multiplied. So, here we get the theta dot value, and of course, there is one characteristic length is there. Then we have a math function, and from here basically I, by putting a gain, I get the Fd value. Okay. So, here this is basically the V square term corresponding to here, and of course, I can always get this theta in order to evaluate the Reynolds number and see the value of it. Okay. So, this way we can do that. Then we can also include, apart from the aerodynamic drag, the friction at the pivot also. Okay. So, as I said, there could potentially be a significant amount of friction at the pivot point, and the Matlab Simulink model including the aerodynamic drag and Coulomb friction at the pivot point can be created again by taking from that basic model. So, these are the basic model which we have already seen. Theta double dot, here we have theta dot and here we have theta. So, sin theta here and multiplied by g by L minus is taken here. Okay. This part is actually added in the previous part. These things are same as the previous one. So, here is basically we take omega or theta dot, and here is the frictional torque and we get a product of it, and then we divide by 1 by ml square, because you see our basic equation we have been dividing by ml square in order to get the theta double dot term. Okay. In the left hand side, and then this can be subtracted here, and we have the theta double dot value coming from here, and this way we can create a Simulink model for the pendulum. Okay. So, this is what I wanted to tell you. We can see the response of the system based on an initial some pendulum angle. We can see the response. These response are decaying. Okay. The magnitudes are decaying, and we can take some value here. I am giving some value for which these simulation have been done. Okay. So, you can try yourself by giving the different values and observing the behavior. Okay. Thank you.